Are you happy, Christian?
Yeah.
So thanks for everyone who's come today for our second postgraduate theory seminar. So today we've got our very own Christian Perfect, he hasn't done this for about a year, but he's come out of retirement to talk about the computability of Bass-Serre structures in the Grzegorczyk hierarchy.
Okay. Hello.
Hello.
There's tea, coffee and biscuits at the back of you.
Oh, is it?
It's all very civilised.
Wow. Did you get money for that as well?
We decided not to use it on the
overdraft.
I guess what you need to pay for with the funds, the travel expenses and speakers.
Yeah.
Don't worry about me. I'll sell
Okay.
you.
Right.
Oh, do you need a what? No, you've got a watch.
I've got a natural sense of time. So, yeah, this is something I worked on for a year or two part-time, and I've given up because the theorem didn't work in the end, and got other commitments. So I'm going to go nice and slowly through computation and then through to all this Greek theory nonsense at the end. I think the one thing I did achieve was making up some nice notation, so that's my first slide. So I'll define recursive functions, which is sort of the basics of computation from like the 50s-ish, and then use the Grzegorczyk hierarchy, talk about lists and trees and stuff, and then finally get onto groups. So it might take ages before we get to any actual group theory. So that doesn't fit, and I'm getting emails. Yeah, so it turns out that you have to be really pedantic about when that means a function. So much of this stuff is just notational nonsense. So a function can have any number of parameters, any number of arguments, or you can make them a vector, and I'll switch between those. When I like to refigure some, often stuff is built up from operators, but then it gets unwieldy using those over and over. So if there's already some decent notation for that, I'll say this notation colon equals whatever the new thing is. And then function raised to n thing is the same function applied n times to itself. There's probably more that needs to be think about. So computable functions or recursive functions are functions on the integers, non-negative integers, which I call n because why not include 0? So they're functions from integers to integers. You can't do anything with floating points. Am I getting what? British Gas now? I wonder how to turn that off. Turn the Wi-Fi off. There we go. Yeah, so you build these up by this isn't going to fit. Why is that not fitted? So you start with 3 functions. They're sort of like the beginnings of piano arithmetic, if you've seen that. So you have a function which gives you 0. That's where you start, the smallest number. You can get higher numbers than that by using the successor function, which just gives you +1. So you never deal with numbers as numbers. You always just have a function that represents that number. So successor of 0 represents the number 1, but is actually a function which takes no arguments, which just represents 1. Then finally, this projection thing lets you mix and match functions with different numbers of arguments. So if you've got a function of 5 variables, you might want to pick out the 4th one to it, or something like that. So P and I takes n numbers, gives you the ith one. So there'll be two ways of combining these to get everything else. Some other computability classes give you more operations, but that's you end up with the same set of things, more or less. So this screen is slightly smaller than the one I tested on. So for composition, just compose two functions. You just need to clear up the notation for that. So if you've got f and some number of functions called g, so f takes n arguments, you need n g's. So f of g1 times gn is that. You say the operator c combines f and all those g's to give you a new function.
The question is because it's would project onto the side of the board, as you might rotate it.
No, it's missing here as well. It's because we haven't upgraded our projectors in 5 years and they're still on a really low resolution. I can try. There we go. Reduce the zoom.
I'm finding that when I'm lecturing on there, students are making a very large screen. They're getting the glare on the screen where that title is, and that composition happens. I don't know if that's how projected on the whiteboard. Maybe it's okay.
Yeah, if you project on the whiteboard, you get a lot of. I really like trying that because then you can draw on top of stuff you're projecting.
Well, that's
But
right. I don't like to draw.
no. Right.
You just need to make some kind of something that's, whiteboard, but also not shiny.
Or you could project all black and just have white text. I don't know. That feels like magic. Well, no, because if you're projecting black, you're just not projecting any light.
As long as I can do that with a couple of lines at the top of my latex, I might be able to do it.
Maybe. I don't know. Right, so composition is an operator on functions which gives you functions back. So you can create a function h, which is the composition of one of your functions. And if you're just composing one function with another, you might as well use the normal notation for that. Okay, so the next operation is recursion, which is where you get into trouble. So recursion is sort of an inductive definition of a function. So you say you add another parameter to a function. Let's say you say it matches some function with nothing, 0, and then for n plus 1 you say what it is in terms of the value for n and whatever these parameters are as well. So I'll do some examples of that in a bit. So that's also an operator, so it needs a name. So you call it, if h is defined by recursion on f and g, then it's r of f and g. So we've got the number 0, we've got something which lets you add 1. So by adding 1 lots of times, you can get to any constant number. Or you can get a function which adds a constant to whatever its input is by composing the successor n times. So that's what that's saying. So that's finitely many compositions. So you're not getting very fast-growing functions doing that. Sort of the gist of the aim of what you're doing with all this is trying to classify functions by how fast they grow. So that's the thing. So addition is repeatedly adding 1, but a variable number of times. So you can't just do it by compositions of functions. You have to do it with recursion. So x plus 0 is x, but then x plus a number bigger than 0 is equal to x plus y, and then you add the 1 on separately, so you just mix it around. So you can say it's the successor of the addition one smaller. you can keep going with the same idea. So multiplication is repeated addition, exponentiation is repeated multiplication. You can keep going up and up and up and up. So if you can do all that, that's fine. You can say what functions are computable. So what functions can you define in terms of composition and recursion. But if you want to think about how long something might take to work out, or how much space you need to do it, or just how complex it is, you want to classify them. And Grzegorczyk classified things by how quickly they grow. So multiplication grows a lot quicker than addition because the graph goes things like that. But if you just counted recursions, that wouldn't really do it, because often you can give a recursive definition of something that doesn't actually grow bigger than the function it built off. So you can have x minus 1 is a thing. So you can say x plus 0 minus 1 is just, sorry, no. So I want to get a function which just takes 1 away from whatever you put into it. But we're only working with non-negative numbers, so 0 minus 1 is going to have to be 0. So that's a base case, and that's why I'm writing minus with a dot on top of x. It's not really minus. So then x plus 1 minus 1 is equal to x, which you can do because that's the value of whatever the previous thing of this recursion was. So that's a recursive definition of a function which grows slower than what we've already got, which was just the identity function. So Grzegorczyk's solution was to classify recursions into bounded and unbounded recursions. Oops. So f is bounded by h if h of x is bigger than f of x for all x. It's fine.
Does that need to be a strict comparison?
You can make it that way just by adding 1 to h. So then if you've got a class of functions c, you want it to be closed under bounded recursion, so you want to get everything you can get by not making the functions grow any bigger. So if you've got two functions f and g, if the result of doing a recursion on them is bounded by another function h, which is already in your class, that's fine. Is that what I'm saying? Yeah. Then that's a bounded recursion. If there isn't an h that bounds that recursion, then r of f and g isn't in your class. So if you've got a class containing addition and everything else you can get by composition, bounded recursions, all that, then you can't get multiplication by bounded recursion because there's no function which is just a composition of additions that is equivalent to multiplication. You can make something that multiplies by a constant, but you can't make something that multiplies by any number. If you think about classes that are closed under bounded recursion, then you can make a hierarchy out of them by starting with just the primitive functions, closing that under bounded recursion and finite composition. So anything you can get by doing bounded recursion or finitely many compositions of functions you've already got gets you this first class E0. And then from then on, you can get bigger classes by starting with en, do a single unbounded recursion on functions from that class, and then close the result under bounded recursion. So if I had the class containing addition, one unbounded recursion would get me multiplication, and then using that can bound everything else. You can get a whole set of new functions which are strictly smaller than multiplication. So if a function is in the class en, you say it's en computable. But
Sorry.
yeah. So you also want to do computation with sets, because sometimes you want to know whether a function can be applied to a particular number. So decide if it's in a certain subset of the naturals. So the characteristic function of a set gives 0 if the thing you pass into it isn't in the set, and it gives you anything bigger than 0 if it is in the set. It's way easier to say just anything bigger than 0 is true in this case than instead of just saying 1, because otherwise you can do a load of work. So yeah, the aim when working with all this stuff is you've got a function which does something on the natural numbers. You want to find the smallest level of the hierarchy that you can make a definition of that function that it fits in. Because you can make a function, you can define it any way out of functions that belong to any level, but you want to find the smallest one. So some facts about the first few levels of the hierarchy. Everything in the first level is bounded by something which just adds a constant on. So you can't do anything like the function 2x definitely doesn't belong to first level. Everything in the next level up is then is bounded by linear combination of its arguments, which I said there. So we're still not at polynomials. So E2 is basically polynomials. And then E3 it contains exponentials and factorials, and is equivalent to the class elementary, which if you're a computer scientist has meaning.
So that wouldn't contain some iteration?
No, that's the next level up. It's like the Newcastle stuff that roughly corresponds to each level of the hierarchy, because tetration is repeated exponentiation.
Yes,
that definition. So once you've got to E3, you can do most things that you want to do. You can do minimization over a set and logical predicates and all sorts of things, prime numbers and so on. So I've glossed over all the stuff that you have to show that various functions live at different levels of the hierarchy. What it boils down to is, once you get to E3, you're fine. So now I want to work on groups and presentations of groups, which means I need a way of representing words. So if I encode the generators of a group as numbers, then a word will be a sequence of numbers, or list of numbers. But we can only work on functions that take one number at a time, so you need a way to encode many numbers as one number, which Gödel did, which I think is the way you do the incompleteness truths is you encode expressions in some logical calculus as numbers, and then prove that they can't be computed. So if you've got a sequence of integers x0 to xn minus 1, I start counting it to 0 for the aforementioned non-Roman reasons. So what you do is you just take the first n primes and the exponent of each one, or the exponent of pi is the ith number in your sequence. And you have to add 1. So when you've got a 0, that doesn't mean that the prime isn't present. So you can then work out how long the sequence is by looking for the first prime that divides your number. Going very fast. This is going to be a half-hour talk. I'm going to leave computability for a bit. So the definition of a graph I use follows Serre. It's a bit peculiar. So you have a set of vertices and a set of edges, but the edges all have to be directed. So I'm not dealing with directed graphs, so whenever any two vertices are linked by an edge, they're linked by an edge that way and an edge the other way. But you need to make sure these two edges are separate things, so we can talk about them like that. So you need two maps to define the graph. You have something which gives you the start and end of each edge, the initial and terminating vertex, and something which gives you, if you've got an edge, gives you the edge in the opposite direction. So if you've got a set of vertices, a set of edges, and these two maps, then you've got a graph. So a path is a sequence of edges, so that the end of each edge is the same vertex as the start of the next edge in the sequence. And a reduced path never has an edge, and then you immediately go back on it, because there's no point in doing that. So circuit starts and ends at the same vertex. Oh, I've said what a reduced path is twice. I put that in thinking I've missed it, and I haven't. So then trees, acyclic graphs, but what we need to do is pick a root for the tree. It can be any vertex in the tree, so you can just think about a tree as it's hanging down from any vertex, and it's still a tree. But you call that one the root of the tree. And then if, sorry?
The root is at the top.
Yep.
That's C.
It's an Australian tree.
Ah, good.
Yeah.
No, it doesn't be the
We had such long discussions about whether that was okay. I was like, I'm just defining it. It's happening. Because I like to draw trees going down that way. Well, no, because they, when you want to add stuff on, you want to go down. If you've got words up here.
They used to pick up these kind of fossilized sequences from the beach, you know? They dry out.
Yeah.
Yeah. And they
Right.
just hang.
Yeah.
Computer science, check on myself.
If you can't pick up trees by the roots and hang them like that, then shame.
Yeah, I mean, a kind of binary thing, right?
It goes round here.
There's some kinds go off as well.
Anyway,
Sorry.
I'm going to be talking about left and right soon. That's going to blow your mind.
It's left on the left at least.
Yeah, it is. Left is also the least.
Sorry, I will shut up.
So you can have a root and you can do all that, but you can embed a tree in the plane any way you like, So I want to insist that there's a certain ordering on the vertices at any distance from the root. So I want to say there's a leftmost one, and I want to say where each one is subsequently. So you can then give numbers to all these vertices by starting at 1 up here, and 2, 3, 4, 5, so on, so on, so on. Because what we want to do is have computable functions which tell you how to get from one vertex to the other. Okay. Do I need to describe what a depth first walk is? Sorry, my phone's ringing. Right, so depth first walk is if you've got a finite tree. Get rid of these numbers. So I did a breadth first walk there. I started at each level, I went from left to right assigning numbers. Depth first walk, you start at the top, and then for each edge coming down, you visit that. And for each, you do it recursively, so you go down again. So this one's 3 now, that's 4. At the end, come back up. This one's got another thing I haven't visited, so 5. So you do that. So you try and go as far down as you can, visiting vertices and assigning numbers to them until you can't, then you come back and fill in the rest. You can do infinite trees with a breadth first walk. It's just a bit trickier to define. I haven't bothered defining the functions that do this, so I could have just said a breadth first tree. Yeah, well, we can't use this. I'm only working on natural numbers. So.
So if this walk is 1, 2, 3, 4, 3, 5, 3.
Yeah, well, it's one.
Because you visited.
Yeah.
It's going to be a walk. You're going to have to visit vertices twice.
Yeah.
But when then you don't really know something.
But so then you say that the label of a vertex is the index of the first time you reach it in the walk.
Yes.
Which you can do.
Yes.
Yeah. Sorry? Probably. Yeah, it's been so long ago I've forgotten how you do this, but yeah, you can do this in many ways. Done it in one. So we've got lists, we've got graphs, we've got trees, we've got all the arithmetic stuff we need. So finally we can do computable groups, which was first tackled by Rabin in either the 60s or the 50s, I don't know when Rabin was around. But he was just looking at primitive recursive functions, so he was just looking at whether a group is computable at all. But then you can very easily just tack on, do these functions belong to a certain level of the hierarchy, and then dealing with Grzegorczyk stuff. So for a group, what you need to have is a unique number for each element of the group. So you need a function I which maps elements of the group to numbers. This isn't a function like all the other functions we've been seeing because its domain isn't natural numbers. And that's where often you need to write, when you're dealing with group elements, I of G1 to mean the number representing G1, but I forget all the time. That's fine. So the only other things that define a group, apart from what's in it, are how things multiply together and what the inverse of things is. So you need function M, which does multiplication, function J, which does involution. So if you've got these three things that match up a group, then that group is computable. What Canonito and Gatterdam did, which is the people I'm building my work off, they introduced a standard index for a group. So if you've got a presentation, you can think about every element as a word, or really there are all sorts of classes of words that are equivalent to each element. So to encode generators as numbers, words as lists of generators, and then multiplication, you could just say word 1 times word 2 is you just stick those words together and cancel. But you need a unique number for what that element represents. So you just look at all of the numbers less than whatever that encodes to, see if they represent a word equivalent to that element, and pick the smallest one. So you're doing bounded minimization to find the unique word that is the least one representing a particular element, which belongs to the class E3. So once you've got some groups that are computable at a certain level, you want to use them to build more groups. Like we had functions, we're using functions to build more functions. It would be nice if you didn't have to start off in the pure land of having a group and then injecting it into the natural numbers. If you had some building blocks, then use them to build up the rest of the groups. That would be good. So two simple kinds of extensions of groups are H&N extensions and free products with amalgamation. For an H&N extension, you slap just a group. So you've got the group G, got two subgroups H1 and H2, and you have an isomorphism between them. So you take two subgroups, identify them using isomorphism phi. So if you'd just done that, that would be like taking a quotient or something, but you want to get a bigger group. So you add another generator T, so that when you commute an element of this thing by T, that is equivalent to some element in the other group. So that gives you a bigger group with some more structure. Or if you've got two groups, actually I'll draw that one. So if you've got a G, fine, like that. I'm going to build into graphs. So if you've got two groups and a subgroup from each and you want to make them the same as each other, you do a free product with amalgamation. So the free product of two groups is, if you've got G1 is generated by an alphabet X1, so its words are all like X1, X3, so on, X1. And you've got another group whose words are letters like Y1, Y2, so on. The free product of those is just the smallest group generated by the union of those generators and with all the same relations on. So you might do a bit in one group for a bit, then do the other one, come back. So the free product of amalgamation, you define a way of moving between the two groups. You say this subgroup here is equivalent to the other this subgroup in the other group. Yep. So you could start with just your two groups are just the free group on one generator each. Make the free product of those gives you the free group on two generators, and then amalgamating subgroups is the same as quotienting out some things, so that gives you relations. So yeah, so that looks like G1, G2, phi there. So yeah. Okay. So Kalanito and Gatadam showed that if you've got a group that's computable at level n of the hierarchy, and your subgroups are decidable at level n, and the function phi is computable at level n, then the H&N extension is computable at level n plus 1. So you have to do an unbounded recursion to compute this group. Sometimes. Sometimes you can construct it so that you stay at the same level, like you take a really trivial set of subgroups or choice of things. But there are cases when you have to do an unbounded recursion. And the same deal for free products and amalgamations. Like what? Yeah. But I'm not.
That's the same as phi being n-computable. It's the n-computable and its characteristic functions.
Not quite. You do need that condition. So.
Because you've got both conditions on the...
Yeah, you do need that condition on both of the subgroups. You've got.
So you do need it?
Yeah. I just forgot it.
Is phi not a characteristic function then for...
No, because the way you define phi could be something really silly, like it just doubles every number. And then the reason it's an isomorphism is because of your choice of subgroups and because of your index. So you need to be really careful at every step of the way that all these functions are total functions on the integer, so you can pass any integer into them. And
right, so phi isn't a group isomorphism. Phi is an n-computable function which is a group
I skipped all that. Yeah, you need to say what a homomorphism is in this context and what an isomorphism is and all those things. So yeah, it's an en-computable homomorphism of groups if it acts on the index of the group and satisfies all the identities that the homomorphism does. Yeah, so Kalanito and Gatadam show that these extensions raise you up one level. Sorry, my phone's going crazy, so my brother might be dying. I've got 7 messages. Oh no, it's just Bill going mad. Right, so I've drawn a vertex, I've drawn 2 vertices joined by an edge, so of course next I'm going to draw a graph. So a graph of groups is a graph like that, why not, with a group on each vertex, so G1, G2 and so on, and then what else? On each edge, remember we have 2 edges for every edge that we really have. We've got one that way and one that way. For each edge, you've got subgroups of the groups at either vertex, and then an isomorphism between them. So you're always, I could have that as well, sorry. So you're doing, like each pair of vertices drawn by an edge is like a free product with amalgamation. But then you're joining them all together to get a massive product. Or you've got an edge that comes back to this, is only on one vertex, then you're picking 2 subgroups of the same group and identifying them, so that's an H&N extension. So that's a graph of groups, if you've got a graph with all these groups and subgroups attached to it. So then what you want to look at is the fundamental group of that. So all, if you can think of words as paths in the graph, and you're doing something in each group as you get to it. That's the fundamental group of the graph of groups. So there are a few ways of formulating that. The one that's most convenient for me is you pick a spanning tree of the graph, so a tree that contains every vertex. No one's red-blue colourblind, are they? I feel terrible that I complain every time about red-green. Someone's red-blue. So that. Sorry?
I think that would be hard, wouldn't it?
I think it's just
Red-
a bit less common.
One of my.
Yellow you can be and red, green or something.
I don't know. One of my maths.
Red, green is very common. I think red blue is possible.
Yeah, one of my maths teachers was red-blue colourblind, and we had badges which said which order we could go into lunch, and you got them confused. So
You could just have
there's an entire year group.
right?
Used to.
I might not see the green things that you're right on the board for that sometimes, but
Yeah. So you might be a bit
And you
colourblind.
could be a dog. You don't seem like
That's not true.
really?
Right.
actually I think
I
that's
would say you see two different colours where they've only got two different kinds of cone cells, so they're red,
Apparently
green,
some
colour.
people are four.
so I'm not quite sure what colours we would use
Yeah.
from those drawings there. Is
I
that blue or
personally
orange?
disagree.
This is blue.
That's blue, I thought it was, but I'm not completely sure. Is that
I might do
right?
extra colour like a-
This other thing's red.
No, I don't think
Oh.
it's red. but-
Yeah, everything was blue until I drew red.
Yeah, which
So
colour
red, green,
is
colour one, they only have two separate cone cells, and the one they're missing is the one.
Okay, I'm going to end this with the best fact. Goldfish can see ultraviolet. Right. So.
Vampires.
I didn't
Actually,
know.
not vampires, they're vampires.
Insects.
They can see ultraviolet. No, not vampire, they can red.
Spanning tree of the graph. I need to pick a root vertex, v0. So every path in the graph is going to start here, do something, travel along the tree, and it's going to travel along the graph, so it might go up there, around there, and back. So trivial paths are ones that only stay in the tree, so we want to make those trivial in the fundamental group. We're going to do that. So the fundamental group of a graph of groups like that is this mental presentation, where you take the generators, all the generators of the vertex groups, and then you add a generator for each edge, so you can represent travelling along that edge. And remember that we've got two edges, so there's a generator for that way and there's a generator for that way. No, there isn't. That's the inverse. Yeah. So then relations are, you get all the ones from the groups, because they only concern those generators. Every edge in the spanning tree becomes trivial. You just quotient it out. You don't care about it. And then we've got these ones which represent. If you start in this group, go back to that one, do something in the subgroup that's associated with this edge, then come back. You might as well have done it in the subgroup that was over here without going along the edges. So E inverse AE is equal to phi of A. So that's fine. So what you're keeping track of is the stuff you're doing to make loops. So up here and around there, you'd get this edge in your word once it reduced down to represent doing that. Then all the stuff that's not in the identified subgroups. Okay. I think I might. Oh, wow. Yeah. So this is the end. I almost had a theorem that when you've got this set up and everything, all the stuff you build it out of is computable at level n, then the resulting fundamental group of graphic groups is En plus 1 computable. So it's not worse than just taking one extension or one food product. You can do as many of those as you like and still stay where you are. I'm pretty sure it's true, because the problem we had with it isn't to do with the structure of the graph. It's to do with we found a problem in the old paper to do with these things. So we were trying to sort that out. So
you can't say the theorem in the old paper is
it's they're really vague. They introduced this standard index thing where you say you've got a presentation of a group. You start with the free group, and then you can get. So you know how to compute the free groups. It's just words, and they reduce really easily. Then if you've got if you've got a set of words that become trivial when you like quotient out something or other, or add some relations, then you can do multiplication in the free group and cancel out bits that belong to this kernel. So they do all that. You can, if you've got a presentation of a group, you can make this standard index. They proved results to do with the standard index, which are fine because you're setting it up nicely for doing computation. Then they had this theorem that whenever you've got a standard index for a group that's en computable, then every index for the group is en computable, which is on the face of it wrong because you can always just chuck in some function from the level up that doesn't actually do anything. But they don't really deal with that and the subtleties of what they actually mean. So it's all really tricky with just working out what assumptions you're making about things. So that's when I got sick of maths and designed. So that's the end. Yeah.
Does anyone have any questions?
I have it's not quite related to your talk, but I was wondering if there's very much known about like how these ENs like filter the class of groups. Or
Groups?
yeah. So like E1 is presumably like the trivial group and you could find it.
I don't think it's been done in that way. Like you can say the cyclic group is E1, of course, and stuff like that. But really, only Canonito and Gattadam did this with this. Like Gattadam did a PhD on this, and then it seemed to just get forgotten. Probably because it's so tricky to work with. It doesn't really tell you very much. Yeah, so they were just thinking about groups that you've got presentations for, and then that's what you're trying to do here, saying when you do certain things to those groups, how many levels up you go.
Do you get quite a lot of groups with most extensions of input cycle?
Yeah. But the class of all groups is way bigger.
So when is the Gattadam and Canonito?
Yeah.
What's the date?
It's the late 60s, something like 67.
Right, so this paper's been around since the late 60s and it's got an error in it.
Well,
Or it's got an unexplained.
it's awful. It's an American Department of Defense photostat. It's been released. It's still got classified stamped on every page. It's been through a photocopier 4 times, and it was done on a typewriter to begin with, so it's really hard to read. And yeah, I can't. No one's really. I don't think there are any citations of it. I don't think. Because he was working in one of those places. Canonito was working somewhere in California that I assume just got funding, so that means it has to go through. It has to get a security classification. I think it's always been public. I can see why you'd get a security person to look at it, because we're talking like cryptography. They're talking about using groups for doing finding trapdoor functions and things.
Is this before they decided that security by obscurity is maybe a last page?
No, what you want is a function that's really hard, and so if you can say how hard a function is, that's good.
Right.
But this one didn't work out. So, yeah, but there's been a lot of work done just on normal functions in the Grzegorczyk hierarchy, like E infinity is the union of all of the levels of the hierarchy, and that is exactly equivalent to the primitive recursive functions, which is what we normally talk about. But then people say bigger ordinals than that, and do you get hypercomputation out of that kind of thing?
So how about the EN decidable sets? How do those compare to the sort of this? How do those classes compare to the sort of classical complexity classes, like sort of language theoretic complexity?
I don't know. I guess the regular languages would be at E3. Does that sound right? If you've got, you can work with lists of things, you can do stacks, and you can do words.
Right, they would be strictly smaller than E3 though, right? Because they're just the regular languages is just constant space.
Yeah. But yeah, I don't know. I need to top up my parking in 6 minutes over fair. Yeah, I don't know. What further classes of languages can you get? Context tree would have to be primitive recursive, would it? Yeah, the context-free languages have to correspond with the primitive recursive functions because it's a recursive definition you get. Is that right? Or?
Well, one of them's function theoretic and one of them's like.
Yeah, but when you're dealing with these functions, they're just like trees of applications, so it effectively becomes we're dealing with trees.
Right. So aren't you really saying that context sensitive is, or is it mildly context sensitive? There's like sort of tree bounding. There's lemmas branching, bounding and branching in trees.
Don't think so. Yep.
So you say that in regular language level precisely you find that space.
Yeah.
And context sensitive is quite precisely in that space.
I think it might even be mildly context. It's one of the types of context sensitive. No, context sensitive. Yeah, that's linearly bounded. Yeah.
Yeah. So, in summary, I don't know.
That's probably needs more than 2 minutes.
2 minutes plus a year and a half of not thinking about it.
Yeah.
Well, I said to Andrew at the away day, should we just chop off the theorem at the end and publish it? Because I've done the work of reading that paper and making it legible.
Well, why don't you just finish up the theorem?
Because it was a knacker. I spent 6 months just on one line of it.
I don't think it just means
Yeah, Andrew thinks it can be done, but just we kept going round and round in circles of, is this one true? No, maybe it is, and then maybe this one isn't. The way Kandanisa and Gatadan do it is this pretty circular logic. So, yeah.
maybe we should have a seminar where you sit there and
Maybe. That would have been, well, follow up to this. Maybe. Yeah. It would be very nice. Well, it's definitely at most 2 levels higher, but I think that you can get for pretty much any construction.
Well, that's a good
So I did offer at one point to just say it's n plus 2 and then we put it on the artifact. Yeah.
And then you have it as a equation. Is it really one? And then you've got a second
This implies a continuing career in research mathematics that I don't have.
Cites your paper. Like the way to get cited is to leave.
Publish nonsense and get it cited.
Publish stuff with
This is why the ref is terrible.
Yeah, it's complete nonsense. I've been talking about it today.
Yeah.
I have to go too because I have to get home.
Right.
So I need